There are many people deprived of certain privileges. Just imagine how someone feels when they lose one limb, or maybe even more. Then try to imagine the joy on their faces after they are able to walk again. It's just priceless. Every person should have the right to live a life without any disability. We should not accept any limitations, but we should overcome them by technology innovation. As a team, we fight to assure these human rights, accepting the fact that humans are not the disabled ones. A person can never be broken, but our technologies are incomplete and disabled so far. We fight our way to provide fully functional bionic leg for people who cannot afford it. It is well known how expensive a bionic leg is right now, but we believe that every person in need should have the chance to purchase something that is used to make their life just normal. It is a tremendous feeling for us when somebody without any hope is able to walk again using a bionic leg. We work as a team to create engineering system using modern technologies. In the first stage, we use electrodes to sense muscular impulses in the residual limb. An electronic control system detects those signals and amplifies them to power electric motors that operate the prosthetic limb as they were real. So, in other words, when a patient thinks, "I want to move my leg," his brain stimulates muscles in the residual leg. The electronic system commands the electric motors to move, and the prosthetic limb shifts accordingly. Our team works with the patient at every stage of the process, from choosing the best prosthesis according to the needs, to the process of measuring, manufacture, and fitting. We help the patient to learn how to operate a new limb and tackle new challenges such as taking up a sport or activity. The final result should be a realistic, good-looking leg. It's true, you can make a difference. Your funds and donations will be used in expensive research to bring up cheap and affordable solutions for everybody. We need funding for developing and optimizing the bionic leg so it is affordable for everyone. The materials and the functions of the leg must be tested for perfect results. Now you can be a part of this process and change lives forever.
I was born with cerebral palsy, so I can't walk at all. And using my wheelchair is limiting. I'm very independent, spirited. I want to go to college, want to be able to do what everyone else would do without a disability.
Several neurological conditions, such as cerebral palsy, spina bifida, spinal muscular atrophy, and even significant head trauma can affect children, causing significant damage in their ability to walk, to balance, and to play.
In many cases, walking becomes very difficult, and they eventually require the use of wheelchairs. This often develops secondary injuries from prolonged sitting and limits their independence.
So many times in school and with friends when people want to go on a walk or go just hang out, you have to navigate so many different things, and then that physical burden becomes a social, emotional burden, because then that kid maybe doesn't want to go out with you next time because it was too hard.
It is well understood that the simple act of walking is the best training for locomotion. Unfortunately, for children with neurological conditions, there is a very small window of time during which they can acquire these skills in rehabilitation.
Because weight bearing is so important for the body, and to get that stride happening, that movement would then encourage her brain to potentially grow and learn to walk.
I think that if I had started super young, like having my body be upright, probably a lot of things would be different. I might be less tight. I might not have as many spasms.
For the past 20 years, scientists at UC Berkeley have been developing exoskeleton systems for individuals with spinal cord injury. These systems are effective at treating adults, but cannot address the rapidly changing needs of a developing child.
Our technology is now poised to address this urgent need. We propose to develop a set of exoskeleton systems specifically for children with neurological disorders, enabling them to develop their walking skills during the critical period of their early development. Our technology will help jumpstart the rest of their lives.
Children with CP and other neurological disorders should be here in the schools playing with their peers. Walking and performing natural maneuvers are the best methods of acquiring locomotion skills.
I want to be able to not constantly depend on someone. I want to have that independence and just go off, do things that would mean so much. And so walking would be unbelievable.
So I remember lying on the tarmac. I think when the ambulance guy came on, I knew that it was touch and go. Basically, I lost my leg in a motorcycle accident. As an amputee, without the best you can have, you do a lot of thinking about everywhere you're going to. What's it going to be like? Do you have to go up and down the stairs? And even standing, having a chat with somebody, it's quite taxing.
Blactchford was nominated for the Royal Academy of Engineering's MacRobert Award for developing the world's most intelligent prosthetic limb. Now, this is an incredible advance in engineering prosthetics because it means that the limb actually adapts to the wearer, and for the first time the ankle and the knee actually communicate with one another.
Lynx is the first truly integrated lower limb system where we sense information from the ankle and we feed it into the knee, and we sense information from the knee, feed it into the ankle.
We've got a central microprocessor controller within the Lynx mechanism, and that controller talks to both the knee and to the ankle simultaneously, and it's that interact that allows both joints to actually interact with each other and actually to synchronize with each other on the various different modes that are actually in operation at any given time.
What it does for the user is to try and even out the load so there's less imbalance within the body, to try to save things like osteoporosis, joint wear, all these things that go on.
There were always modular systems, but never someone has thought about the whole limb and how to integrate that. So we had to define the whole messaging. What are the important messages that need to be between the different joints? How should this message structure look like? What communication do you exchange? So it was a completely new field. And we did quite a lot of trial with amputees as well to find out what exactly is needed.
Here was an opportunity to literally get every champion from different projects come together. We had people who deal with industrial design, we had people who were prosthetists, we had software development engineers to the user interfaces, and this whole team had to work together, and that was probably one of the most exciting things I have done in my very odd years of career in this industry.
What's happened in creating Lynx is that above-knee amputees will benefit from technology which hasn't existed previously. You know, we've almost raised the bar to a different level. And before, the products were very much thought of as individual elements in the design. We can suddenly explore lots of new opportunities.
This is an incredible piece of multidisciplinary innovative engineering at its best. Pretty much every aspect of the prosthesis has had to be re-engineered in order to make the Lynx the success that it actually is. 45,000 people in England need lower limb prostheses, whether it's from road traffic accidents or due to military service or because they have diabetes. And this incredible innovation in the Lynx, which allows the wearer to adapt to the terrain, is going to be incredibly important for them going forward.
Just the other day, somebody said to me, "Oh, have you been squatting today?" And I said, no. And I said, "My leg." He said, "What's wrong with it?" there's no leg, and he didn't believe me. I had to like pull it up and show him that, look, there's no leg there, and I see him every day at the gym, and he never knew.
The human foot is made for comfortably and effectively transferring our weight and forces for walking. Following amputation, a prosthetic socket must mirror this behavior in a way that avoids pain and skin breakdown. Prosthetic sockets are traditionally rigid carbon fiber and plastic shells that do not mimic the human body. Lim Innovations has addressed these issues by introducing the Infinite Socket TT, a custom molded and dynamic socket system. The combination of a modular frame and advanced pressure distribution systems enables clinicians and patients alike to adjust the socket on demand. The biomechanics and concepts of the Infinite TT are designed in response to activity demands, pressure areas, and shape change of the amputee's residuum.
Every aspect of the Infinite TT was designed and engineered with the user needs front and center. Other socket designs and traditional sockets cannot adapt and change as the body changes, and they do not mimic anatomy. Here are some of the exciting features of this product presented to you by some of my esteemed colleagues at Lim R&D.
The TT frame was biomechanically engineered to work with a variety of limbs. The frame is made up of 3 modular and thermoplastic carbon fiber struts that connect to an adjustable base plate. Custom molded and can be remolded and adjusted to accommodate volume and shape changes of the residual limb. The hinging posterior strut opens for easy donning and doffing. The entire frame assembly can be slid anteriorly or posteriorly with side axis set screws for fast relief to bony prominence or otherwise optimized fit on the fly. The base plate has built-in rotational side controls for maximum alignment versatility. Perhaps even more important than all the built-in adjustment capacities is the fact that the struts are designed to have an appropriate amount of dynamic flex response.
Seal-in suction suspension or pinlock suspension are modular, exchangeable, and integrated into the Infinite TT. The pinlock version includes an anti-rotational feature built into the funnel.
The abrasion-resistant and low-friction textile layer combines with a remoldable thermoplastic material to provide structure and a custom anatomical fit. The integrated height-adjustable system is cushioned and equipped with air bladders to improve pressure distribution and protect sensitive areas. The Lim air bladder system is designed to evenly distribute pressure regardless of volume change, and is constructed with high-strength textiles for improved durability.
The hinging posterior lift assembly, patella tendon bracing system, and inner textiles combine with a BOA closure system from Click Medical to provide anterior and posterior adjustability and lift to reduce end pressure. This assembly is also designed to draw in the medial and lateral walls for improved biomechanical control and support that can be increased or relaxed per activity. It is designed to provide an optimal fit for the patient that can be adjusted for various activities, daily volume change, and eases donning and doffing of the socket.
The flexible outer cover is designed to encapsulate the frame's proximal components, protect the user's clothes, and to provide a low-friction layer with an aesthetic finish. It's currently available in 2 colorways, black or blue exterior with Lim blue lining. The cover is removable and washable.
Now, people with below-knee amputation can get a socket that can change and dynamically move with their body. With this anatomical and user-centered design, people are consistently telling us that the Infinite TT allows them to do things like go up stairs and ramps with greater ease than ever, or that they can now ride a bike when they could never do so before. But don't just hear it from me, hear it from the users themselves.
In a nutshell, this thing is nothing short of amazing. I've been able to do things already that I haven't been able to do for an entire year.
The fact that it has give to it, you know, it's almost like a living part of you as you're walking. This thing actually has just enough cush to it that you're unaware of it. You're not as aware all the time that you're wearing a prosthetic or that you have an issue.
This socket is, well, like no other. I love it because it's comfortable and I get to control the comfort.
Well, with the Lim Innovations socket, it just feels so much more natural, and it's an intimate fit that you can adjust.
With what I've seen already just in 4 full days of wearing this, this has been spectacular.
The really neat things about this too is it fits so well that I'm more aware of where my foot is in space, especially when driving a car with a clutch. I have feel with this socket,
that I didn't have before with the hard carbon fiber. I had to look down to see where my foot was.
My favorite function about this is the BOA and the air bladder. I do a lot of fast walking, so after a while I might give it a couple of twists, you know, and then I'm good to go.
It reaffirms your faith that you can get your life back.
Yeah, I was a very strange child. I would sit in the basement, no sound, silence, and I'd just sit there and rock. And I'd do this for hours and hours and hours. I think my parents thought I was insane, but what I was doing is imagining futures, imagining what life could be.
The next step in human evolution may not be biological, but technological. By merging ourselves with machines that augment and enhance our physical and perceived realities. But this is no small feat. I mean, the human form is a product of billions of years of natural selection. And that's why innovators like Hugh Herr are actually looking to nature for inspiration to bridge the gap between man and machine.
When I was 17 with my climbing partner Jeff Batzer, we ice climbed Huntington's Ravine on Mount Washington. We got disoriented in a complete blizzard and spent the next several days trying to get ourselves out to civilization. We made it within a few miles of a roadway, and we couldn't walk. Our lower limbs were completely frostbitten, completely numb. Luckily, someone was out snowshoeing, saw human tracks, and we were plucked from the mountain via helicopter. Then I spent, months in the hospital. Gangrene had set in, was slowly making its way up my body, and it was clear that amputation was necessary. About 12 months after my limbs were amputated, I was climbing at the same level as I had before the accident. And people started to get nervous. And then I exceeded that level and started to climb walls that no one ever climbed before. And then I became a threat. And that happened overnight. Some of my climbing colleagues actually threatened to cut their own legs off to achieve the same unfair advantage as me. No one actually did it. The fact that I could design my body part and exceed what I had achieved before and even exceed what nature intended was very inspiring, because I realized that technology has the power to heal, to rehabilitate, and to even extend human experience and human capability. That set me on this trajectory of tinkering, of designing, of climbing, and then going back to the shop and whittling and carving and machining. I mean, my closet looked really funny. You didn't see shoes, you saw all these bizarre limbs and feet everywhere.
So what sets Hugh's legs apart from the rest? Most prosthetic legs are passive, and as a result, amputees have to use about 20% more energy when walking with their prosthetic leg. Hugh and his team studied how our leg and ankle naturally work to create their bionic counterparts.
So our key strategy in the design of bionic appendages is to look into nature. So we studied how the calf muscle works, for example, and how the calf muscle is controlled by the spinal cord using neural reflexes. And we programmed that capability on the small computers that are underneath the shell in the bionic limb, so that when I walk at different speeds and different terrains, it's constantly updating the stiffness and power it's providing me.
The motor mimics our calf muscles, adding positive force to the prosthesis, and that propels the body forward. This is especially helpful for walking up ramps and stairs.
So that even though the limb is made of titanium and carbon and all these synthetic materials, it moves as if it's made of flesh and bone. The value of closely respecting the biophysics is that when we fit this prosthesis to a human body, there's often no training, because the human body remembers how to walk.
Oh my God, I can't believe it! It's just like I've got a real leg.
That's the value of this biomimetic design approach. We built our first foot ankle in 2002, so it's been a long iterative process. Probably 30 fundamentally different designs that led to the bionic limb as it exists today. We're studying how the tissues in this part of my body, how stiff they are. We're studying how the skin moves. And we then 3D print structures that emulate those tissue properties.
It looks like a topographical map of your residual limb, and it makes for one of the most comfortable sockets available today. Besides the physical attachment to the prosthesis, Hugh's team is working on a way to control bionic limbs more naturally. They've developed legs with EMG sensors that measure and decode the electrical impulses in the muscles of the residual limb and then translate that into movement. Thus, the user only has to think about moving their leg to activate the bionic limb.
I have the condition that my limbs are amputated, but that condition, because of great technology, I have the quality of life that I seek. Extending that story across all of humanity, one can imagine a world in which technology is so remarkably great that we can eliminate disability. And I believe that will happen in this century. The twilight years of this century, there will be no disability in the world.